for coming back. And so now I will pass to the second part of the talk, and this will feature more algebra for sure. So I will need to maybe start by telling you what a unimodular ribbon Hopf algebra is. I won't provide details for definitions. I will mainly fix notations, introduce names, and give concrete examples. So you see what these pieces of structure look like in concrete examples. So we start from the notion of Hopf algebra. And I should say we met the term Hopf algebra already twice. One is in this statement here, and the other related to this construction. In this case, we're talking about a Hopf algebra in the usual sense. In the previous slide, here we had a pre-modular Hopf algebra. This is a notion that arises inside a more general braided monoidal category. And these two notions are very closely related. There is a very precise relationship between the two, but they're not directly one the generalization of the other. So I will try to explain a little bit these two variants. So we start from the classical one. A Hopf algebra, you might have encountered it many times before, is an associative unital algebra H over a field K. So it comes with a product, with a unit. The product is associative. And it also comes with a structure of a co-algebra and with an antipode. So it has a co-product, which is a linear map from H to the tensor square of H. And I will use this notation, which is a very common abusive notation introduced by Sweedler, I think. So it's an abusive notation in the sense that we should have a sum here in general. So the co-product of an element is not always a pure tensor, but this is a notation that's very widespread. I will use it for the time. Then there is this algebra admits, so this co-algebra admits a co-unit, which is a linear map from H to the base field. So every element in H has a scalar associated to it, which is its co-unit. It has an antipode. The antipode is an automorphism so it's an anti-automorphism as an algebra, but it's an endomorphism as a linear as a vector space of H. And unfortunately, the structure doesn't stop here. We will consider ribbon Hopf algebras. So a ribbon Hopf algebra is a Hopf algebra with a very special element in its tensor square, which is called an R matrix. And here again, I'm abusing notation a little bit. So this I here is supposed to denote the fact that this is a sum in general. This is a linear combination of vectors of this form. A ribbon Hopf algebra also comes with a distinguished element. It's called the pivotal element, which is a group-like element in H. And we're almost done with the list of names. A ribbon Hopf algebra is unimodular if it also comes with a so-called two-sided cointegral, which is an element in H, and the left integral, which is a linear form on H. So this
pivotal element, what is it?
So a pivotal element, so I will tell you a little bit what these things do from a representation theoretic perspective. So the pivotal element, by definition, is a group-like element which implements the square of the antipode by conjugation. The R matrix is an element in the tensor square that can be used to implement non-trivial braiding in the category of representation. So from the point of view of representations, we could consider the category H modules, which is what we need to do there. And all these pieces of structure allow us to equate the category of H modules with some very rich structure. So, well, since H is an algebra, we can consider this category, and then since we have a co-product, we can define So H mod admits a tensor product induced by the co-product. So acting with X on a tensor a product of representations is by definition implemented by acting with the components of the co-product on the two representations. Then the co-unit allows us to define a tensor unit for this in this category. The antipode ensures the category comes with the notion of duals. So we need the antipode in order to define the dual of a representation. Then the R matrix defines the braiding. I won't give details. So an option I had here was to devote several slides to giving you precise definitions for all these pieces of structure. I think it's probably better if I instead give you a concrete example for SL2 for all these things, and then I will tell you in the algorithm how to use all these data to cook up the invariant. So, as I said, the R matrix implements the braiding. So, it kind of, if you multiply using the R matrix vectors in a tensor product, and you flip their order, you would get a coherent braiding on the category of R modules, and this allows us to kind of interpret crossings in diagrams, very roughly speaking. I will.
Do you assume algebra to be quasi-triangular?
Yes. The R matrix is yes. So it's quasi-triangular, and not only it has a ribbon element. So.
The ribbon element is related to the R matrix.
Yes, right. So the ribbon element is cooked up starting from the R matrix and the pivotal element. So in fact, the ribbon element. Another way. So in fact, I should say probably this thing. So because I was writing that the pivotal element gives you the twist, let me maybe be more precise. There is a ribbon element. Since you asked, it means you know the guy. So if you consider this element, which is defined starting from the R matrix and the pivotal element, this is the ribbon element, and this allows you to define a twist in the category of representations. So a lot of structure. This means that H module is a ribbon. And starting from a ribbon category, so in the version of this theorem that was on the slide during the first talk, I was talking about ribbon categories. So the relation between this statement and the one that was on the slide is through this kind of machinery. And then integrals and co-integrals are very important elements. They have their algebraic theory, but in our setting, they will. I'm claiming you should think about them as lambda will be used. So this is no longer for this interpretation in HMOD, but lambda will be used to encode one handles, well, lambda, capital lambda, and lowercase lambda will be used to encode two handles. So
one of them is two-sided and the other one is on the left?
It's a good question. So two-sided, so unimodularity. So here these guys satisfy a bunch of axioms I am hiding. So unimodularity means this guy, which exists. So a one-sided cointegral exists every time H is finite dimensional. So it's sufficient to be finite dimensional to have either a left, so both a left and the right cointegral. It is two-sided if any of the two is invariant under the antipode, and they coincide in that case. And unimodularity is this condition. And in examples, like for UQSL2, the co-integral turns out to be invariant under the antipode, and the integral in general is not. The integral you need either to choose a left one or a right one. There is a very straightforward relation between the two. Like they are related by the square of the pivotal element. but in general they are different. And but there will be, so what I claim is that the notion of pre-modular Hopf algebra in a categorical sense that is coming up appeared on the preview of the algebraic result by Bobcheva and Piergallini. That notion there, which is more categorical as a second, has more symmetry to this. So both are two-sided in that instance, and the reason is, so I will tell you more about why there is this kind of this is not symmetric to the structure, and it will be later. Right. So this is a heavy slide with a bunch of notation. Let me give you some.
Finite dimensionality you do not require?
Yes, it is. So asking unimodularity implies asking finite dimensionality.
If you take the thing, for example, of a finite dimensional algebra, so does it have a two-sided integral co-integral, not necessarily?
So I think. So I'm not sure. I would say yes. So I think the yes. I would say so. So the co-integral exists every time it's finite dimensional, and then you need to check. So to have it two-sided, you need to check that the antipode is yes. So this is the question. So I think yes. I think this is the case. I might be wrong because I never worked with Brinkel doubles, but I think this is the case. Okay, so anyway, let me give you an example where this all holds. Everything is met. So the example is given by the small quantum group of SL2, which I gave you a preview of earlier. So we fix Q to be a root of unity of order R, and R again is an integer which is at least 3. And we also fix this kind of R prime that is either R when R is odd, or it's R over 2 when R is even. Okay? Then UQSL2 as an algebra is defined as the algebra over complex numbers with 3 generators, E, F, and K, and with these well-known relations. So, well, at least the second line is, I think, well-known. The first one is what determines the small version of the quantum group. Maybe not everyone is familiar with this version. So this is what ensures finite dimensionality, essentially. So E and F are nilpotent generators of order R prime. K is a quasi-idempotent, so it has order 1. R prime. Then these are the quantum version of the SL2 relation. So conjugating E by K gives you Q to the power 2 times E. Conjugating F by K gives you Q to the power minus 2 times F. And the standard bracket between E and F, so the commutator, is given by this quantum version, so K minus K inverse over Q minus Q inverse. Right, so this is an algebra, a finite dimensional one. It admits a Hopf algebra structure, which is very well known. These are the formulas for the co-products of the generators, for the co-units of the generators, and for the antipode of the generators. And as I mentioned here, so up to here, these pieces of structure ensure that UQSL2 modulus is a rigid monoidal category. So it's a monoidal category with duals. Very good. Then we can provide this category with a Ribble structure. So this is just a reminder of a very common notation about quantum integers. So curly bracket of A is Q to the power A times minus Q to the power minus A. Then the ratio of curly bracket of A over curly bracket of 1 defines quantum A, and the quantum factorial number is this product of quantum integers between A and 1. Right, this holds for every A in N, and this allows us to define the R matrix. So the R matrix is this, which gives the quasi-triangular structure. It's this finite sum in the tensor square of UQSL2. Maybe the main point of these formulas is not to absorb all the details and to remember everything. It's just to show you that we have very concrete examples. Of course, I could give them. I could give you formulas for general Lie algebras. I chose to focus on the simplest family for today because formulas are prettier and simpler. Right. So this is the R matrix, and the pivotal element is very simple. So it's just the generator K. This, if you, and so what I said before is that if you conjugate by K, you obtain the square of the antipode. So the square of the antipode is implemented by conjugation with respect to K. And
don't look like elements in the algebra, so
it's
all vectors and powers of K.
yes. So UQ SL2 modulus now is a ribbon category with these structures. Right. And now formulas for integrals and co-integrals. So I think the names come from the analogy with well, I don't know. At least let me give you the definitions, the defining formulas here. So if we first set R second to be a number that further depends on the arithmetic properties of R, so it's R over the greatest common divisor between R and 4. And the co-integral, so forgetting about this coefficient in front, you should just remember that it's the product of the highest powers of E and F, and it's a linear combination with all possible powers of K on the right here. And you should sum over all of them. And right, so maybe I could write what are the defining relations for integral and co-integral, since maybe these are the pieces of structure that might be the least known of all. So a two-sided integral, it means that if you do this, you get this. So two-sided means that product both on the right and on the left is fixes the co-integral and brings out a factor of co-unit of x. And a left co-integral is a linear form satisfying this. And I claim that this kind of algebraic relation is what ensure that encoding two handles with lambda gives something which is invariant under Handel slides in some sense, and this gives invariance under cancellation and of one handles with two handles.
Physically, is it satisfying this property as well?
No, the co-unit. So sorry, this one. No. Right. So the co-unit does not satisfy this thing. In fact, integrals are so the space of integrals is one-dimensional. So there is only one. And this is the formula. So it's not the co-unit. So what I claim here is that this capital lambda satisfies this thing. So if you multiply by anything, you just either get, so if you multiply by generators, by either E or F, you get 0. And if you multiply by K, you're fixing the guy, which is kind of reasonable if you look at the shape of this. And the left integral, so to define the left integral, I define it over a basis. So this is a Poincaré-Birkhoff-Witt basis for this quantum group. And this is, and the integral has a very simple formula. So it kills all basis vectors in a Poincaré-Birkhoff-Witt basis like this one, except for the highest power of all the generators. Right. And this is a unimodular ribbon category. Well, it just means that it's finite dimensional, so we already knew this before, but this is fixed by the antipode. So if you do the antipode of this guy, you get back the same. So yes, so this is kind of the examples you should keep in mind when thinking about this kind of construction. Very good. So now I will maybe tell you something about. So I will move on to the variant to a variant of this this notion of unimodular ribbon Hopf algebra, which arises. So I think it naturally arises in the category of four-dimensional two-handed bodies. It also arises from a well-known construction that dates back to the 90s, which is due to Magé, which is called the Transmutation, and it's kind of starts from the question of whether. So the point is, if H is finite dimensional, it can be realized as an object inside H modules. You have several structures of representation on H itself. You can consider the regular representation, the adjoint representation, and stuff. And product unit, co-product, co-unit, antipode, all these, you can ask whether the ones giving you the standard definition of a ribbon, of a Hopf algebra, if they are morphisms in this category, so if they are H intertwiners or not. And it depends, of course, on the representation structure you consider on H itself. And it turns out that if you consider the adjoint representation, almost everything is, except for the coproduct and the antipode. So the reason why we consider a slightly different variant of this notion in a more general context of ribbon categories is because these will not meet exactly the criterion. So if you pass to this category, you need to tweak a little bit some of the structure. So the properties of the more general definition I will give now will not be precisely the same. So the axioms will not be precisely the same. I will tell you, so I will show here those which coincide. Let me say this. So let me start. So now I will tell you what a pre-modular Hopf algebra is. I will tell you something about this. And let me start from what a braided Hopf algebra is. And this is an object inside a braided monoidal category. So the relation with the previous definition would be if you think about C equals vector spaces. And this is a monoidal category with tensor product of vector spaces, and it is trivially braided by the symmetric flip, by just switching the order of vectors in a tensor product, right? So this is trivially braided monoidal category. And so a braided Hopf algebra in C in general is an object equipped with structure morphisms. So a product, a unit, a co-product, a unit, and an antipode. So these diagrams represent morphisms in the category C. Again, you should read them from bottom to top, and you should read tensor product as horizontal juxtaposition, and composition as vertical stacking. So this is a product. So this is a morphism from H tensor H to H. Then the unit is a morphism from nothing. So this is a tensor unit of the category to H. The coproduct is a morphism from H to H tensor H, and so on. This is an endomorphism, this is a right? And the relations I didn't give you before that are satisfied by these pieces of structure of a Hopf algebra, for the moment they coincide with this more general notion. So this tells you that the product is associative. This tells you that the unit is indeed a unit. So if you do the product and then the unit on one leg, you get the identity. So this represents the identity. Then you have co-associativity and co-unity for the co-algebra structure. This is also satisfied. And then these are kind of bi-algebra relations. So they impose a compatibility between algebra and co-algebra structure. It tells you essentially that these morphisms, so for instance, co-algebra structure morphisms are algebra morphisms, stuff like this. And maybe the only point I attract your attention towards is the fact that in this version of the definition in the braided monoidal category, what would be the original definition for compatibility between product and coproduct features of braiding. And this is a braiding in the category C. And this is what requires us to change some structures when we pass from vector spaces to H modules. But anyway, so this is kind of a bi-algebra, then this is the defining relation for being an antipode. It means that if you do the coproduct, then antipode on one leg, and then multiply together, you get co-unit and then unit, and the same on the other leg. And there are more axioms. So there is also more structure because I will because a pre-modular Hopf algebra is a braided Hopf algebra like we had before, but with further additional structure morphisms. So the ribbon element, as I explained before, is cooked up from the R matrix and the pivotal element. So it's kind of a feature of this more general definition that we don't axiomatize the R matrix and the pivotal element themselves. We axiomatize just the ribbon element. And the ribbon element, yes, so it's a morphism from the tensor unit to H, which is a central element, so multiplying on the left or on the right is the same thing, and it has a trivial co-unit, so it has co-unit 1. So empty diagram means scalar 1. This tells you that the co-unit is 1. It's fixed by the antipode. So all these things are satisfied by the standard version of the notion of a ribbon Hopf algebra. But there are other axioms I am hiding here because they are very good. So they are huge diagrams, so I won't draw them here. That were found by Bobcheva and Pergolini, and even before their work, the two notions, kind of a pre-modular Hopf algebra and the notion of a unimodular ribbon Hopf algebra in a classical sense, they kind of diverge here, from here onwards. But anyway, so this is a ribbon element. These are kind of the axioms for being an integral and a co-integral. You can understand these two equations as being encoded by these diagrams. So this is an integral, right? So an integral, if you do the coproduct and then you act with the integral, you compute the integral on the left, on the right-hand guy, the same as first doing the integral and then the unit. So this is kind of the first equation. And the second equation about the co-integral is this one. So for the moment there, I'm only asking this is a left co-integral, so I'm only asking this equals to this. There. But as it turns out, there are other relations which I'm hiding there. But anyway, I won't have time to it's not probably a good idea to give you all the defining relations. Just to let you know that there are plenty of them, but there is an explicit list. So I'm not hiding too many of them. I'm just hiding some ones that would take a lot of space. So there are more. Anyway, so this is a pre-modular Hopf algebra, shortened, and now this is what I was mentioning before, that there is this kind of transmutation operation that would transform a unimodular ribbon Hopf algebras like quantum SL2, the one we were starting from, the small one. So if we take a unimodular ribbon Hopf algebra, then H is not in general a pre-modular Hopf algebra in the category of vector spaces. So the axioms I was hiding fail for the classical definitions. What you can do is you can consider the adjoint representation. So as a vector space is H itself, and the adjoint H action is defined as follows. So it's kind of a Hopf algebraic analog of the adjoint representation in group theory. So you do first the coproduct, you act with the left component on the left, and with the antipode of the right component on the right. This gives a well-defined structure of a representation on H itself, and as it turns out, the adjoint representation is a pre-modular Hopf algebra in H modules. So this is kind of the relation between these two notions. We start from a unimodular Hopf algebra, we transmute it. And transmutation means taking the adjoint representation as an object and modifying these two, so coproduct and antipode. So the community is good, and also product unit. All the rest is good, integrals. Just need to modify these two.
And what's the product in this object?
The product is just a standard product.
As a Hopf algebra, so the product is the product in H.
Yeah, so the product in so the product for it would be a morphism from adjoint representation to adjoint representation. Sorry, this thing from adjoint tensor adjoint to adjoint, and it sends x tensor y to. So this is a standard product. The unit is the unit. So what changes? Maybe let me write down formulas for what changes. I have them here because otherwise. Yes. So right. So I will underline for the modified version is underlined. So the modified coproduct. So maybe I take more. So the modified coproduct is this guy, and these were first discovered by Majid in the 90s, I think. So very early on. So you see, the R matrix intervenes in this modified version of the coproduct, and the antipode is this guy. The fact that the R matrix intervenes in these modified pieces of structure will imply that not only the usual cointegral stays two-sided cointegral, but the left integral becomes a two-sided integral in this braided version of the structure. So with respect to this coproduct, this becomes two-sided. Okay. Right. So now the adjoint representation is a pre-modular Hopf algebra. Now I can come back to the slide I gave you a preview of in the first talk, and the claim was that if you consider the solid torus, or equivalently, so the solid torus is an object in 4HB. In curvy tangles, you should consider the natural number 1. So it's a genus of the solid torus. And if you consider these structure morphisms, they satisfy the axioms of pre-modular Hopf algebra inside this braided category. In fact, they completely freely generate the category as a braided category. Okay, so one thing I could do, maybe one thing I could do now, is to, for instance, show you, because yes, I was quicker than I expected. So maybe let me give you a proof, for instance, of one of the defining relations. So let me show, for instance, that the antipode is indeed an antipode. Okay? If you have questions, please ask.
What do you denote by the little dot?
So these are so curvy tangles have components of different kinds. They have dotted ones and undotted ones. These ones like represent one handles in four-dimensional handle bodies, and the undotted ones so here we have no closed undotted component, but if we had some, they would represent two handles. These encode different topological data. Right. So let me give you maybe a proof. So just recall that the antipode axiom tells you that if you do the coproduct, then the antipode on one leg, then the product, you should get co-unit and then unit. So let me maybe start. So let's see if I manage to do this. We start from like this. So I claim that this is what you get when you start with the coproduct. Then on the left leg you do the antipode, and so if you really glued this guy to this guy, you would get an additional one handle. But I showed you before here on the blackboard that that in fact if you actually did the composition, then you would be able to slide this guy along the middle undotted component and then just remove the two. So I claim that if you do the actual composition, then up to sliding and cancellation of complementary 1 and 2 handles, you would get exactly this picture. So we start from this one, right? And then we do just an isotopy. Right, so what I did here is just I brought this little curve down, and now I can kind of do a Reidemeister 2 move here. And this would give me this. This guy here. And now this I can just flip behind and bring above. So in the end I get this guy. This is just the co-unit followed by the unit, and it's nice to play with all the defining relations and these generators and check that. And this is kind of yes, it's an awesome result. They all meet very algebraic relations. So this is nice. Okay. Very good. So maybe let me give you an algorithm for computing the invariant, and then maybe I will stop a little early. Okay. So as it was asked before, one way of defining the invariant would be, so for a Hopf algebra would be just to say, so actually this is the way it is defined. The way it is defined is you send the solid torus to the adjoint representation, and in general you send the number m to adjoint tensor power m. And then you send generating morphisms to, well, this guy you send to the product, and the product is just the standard one. X tensor y becomes xy. The unit is just, you send this to the unit. The coproduct is the formula that was here before, so you should send to the modified one. Co-unit is standard, antipode to the modified one, integral ribbon element, and co-integral all to the standard ones. You do this, you get a functor. This is a well-defined functor. Now, instead of telling you to compute things like this, let me give you another algorithm that just uses combinatorics of elements of the quantum group sitting on a diagram for a handlebar. Right, so you consider a unimodular ribbon Hopf algebra H, and you consider a closed Kerbitangle T. So closed Kerbitangle just means that it's an endomorphism of 0. So it doesn't have arc components. It's just a bunch of dotted knots and a bunch of undotted knots. Right. So the first thing you do is you insert beads. So beads are these kind of little beads sitting on strands of your diagram, and they are labeled by elements of your quantum group, of your Hopf algebra. So you first insert beads labeled by components of the R matrix around crossings. This is because the R matrix behaves so gives a well-defined braiding. And braidings are usually efficiently encoded by crossings in diagrams. Right, so what you do is, if you see something like this, let's call this a positive crossing, so we choose an orientation from bottom to top of our diagram. So we don't orient our diagram, but we read it from bottom to top, so we distinguish this configuration from this one. And in this case, we place the R matrix on the two components. In this other case, this is kind of the inverse of the R matrix. We place elements of the inverse of the R matrix on around crossings. And we pass to a singular version of the diagram. So we kind of, from this moment on, we forget the difference between over crossings and under crossings, okay? Because this will be encoded by either this choice or this choice from now on. Second thing we do is we insert beads labeled by tensor power, so co-products of the co-integral, replacing dotted components. So every time we have a dotted component, we arrange everything that pierces a cipher disk for it. We arrange it in this configuration, so just vertical strands locally around this undotted component, unknotted component, and then we compute, I don't know, let's say in this case, if we have k strands, we compute the k co-product of the co-integral, and we place beads with components of the co-product on each strand. Okay, and suppose we have 0, so just like an empty product is the unit, an empty co-product is the co-unit. So if you had a dotted component without anything passing in between, you would get a coefficient of epsilon of lambda in front of everything. You just remove the component and multiply everything by epsilon of lambda, which, by the way, is 0 if H is not semi-simple. So every time you see this in the case we care about, you get 0. Right. So, but anyway, you do this. Then what you do is you will have a diagram that will have beads all over the place, right, on all strands. You need to collect for each component beads all in one place. You choose your favorite place and you slide beads along the diagram, and as they pass maxima and minima, they might get an antipode. So if you turn in the clockwise direction, you get an antipode. If you turn in the counterclockwise direction, you get an inverse antipode. The inverse of the antipode. So, but this is just, you have, let's say, so this is not a closed tangle, but suppose this is closed somehow, you slide beads, or you choose your favorite place and you slide all the R matrix components and the co-integral components all in one place for each strand. Passing crossing costs nothing, so just transverse. Yes, so you don't care about crossing, and then you multiply beads together, following this rule. So if you read from bottom to top, you multiply from right to left. And then you will end up with a bunch of components. These dashed parts indicate that they might all be knotted together in a singular version, but you don't care about this. What you care is that you have, let's say, k components, and on each of them you have a single bead carrying a label given by an element of the Hopf algebra. And now what you do is you compute the integral of all these, and you take the product, and you shift. You need to shift using the pivotal element. And the degree to which you shift for each component is given by the Whitney degree of the corresponding component. So what is the Whitney degree? You should start from the place where you collected beats. You should move upwards from there. And then you should compute the total turn of the tangent vector as you move along the whole component and you go back. Right? It turns an integer number of times, and you take this integer number of times and you subtract 1, and this is the power of the pivotal element you need to shift your element xi by. Then you compute the integral and you multiply everything together. So this is kind of the recipe for computing the integral. Right. And I've given you all the ingredients to do this. Now, the formulas I've given you are complicated, so as soon as you get several copies of the R matrix, things become quickly hard to compute by hand. This is something that will need to be. So then the final slide, maybe I will give you some formulas for further simple manifolds where you can do explicit computations very easily, very easily. So again, so if you look at CP2, and so you look at CP2, but you need to remember that you're removing a 4-handle from it, so you're looking at a 2-handle body version of CP2. Then you can see that the result, so the invariant depends on the arithmetic of the order of the root of unity. So when R is odd, it's this number. When R is congruent to 2 modulo 4, then it's kind of similar, but this here is a Jacobi symbol of 2 modulo R prime. Okay? So you have some, and these formulas come from Gauss sums. So you have a lot of Gauss sums in these computations. Then if it's and these two cases are the factorizable cases, right? So in these two cases, you're actually computing a 3-dimensional invariant of the boundary of your 4-dimensional handle body. But in these two cases, you're computing something else. You're computing a 4-dimensional invariant. And for instance, this 0 here could never arise in a 3-dimensional case, because this category, this manifold is represented as a Kirby tangle by this, right? And and when you're representing 3 manifolds, you need to freely be able to add or remove components like these, because this is something that changes the underlying 4 manifolds but does not change the 3-dimensional boundary. So this is something that you usually freely trade in 3-dimensional topology. And if you got a 0 for that guy, you would not be able to do this, of course. It should be an invertible number. So this tells you really that you're doing something for the 0. And for S2 times S2, which is represented by this, S2 times S2 minus 400, which is represented by this diagram here. Again, the result depends on the parity of R, the parity of R prime, actually. So one interesting thing is that, yes, so S2 times S2, so this diagram here, if you interpret it as, if you look at its the boundary of this 4-dimensional 2-handle body, this is, again, S2 times S2 minus a 4-handle. So this would compute in a 3-dimensional setting the dimension of, so in a 3-dimensional setting, you're doing essentially a TQFT here. So this computation would give you the dimension of the vector space associated to the sphere, and this you always want it to be 1. And you see that in the factorizable case, when r prime is odd, this is 1. And in the non-factorizable case, this is -1, and this is not the dimension of a vector space. Right? So, well, I think this is all I wanted to say. I will stop here. Thank you for your attention.
Questions or comments?
So now if you act on some special module of QSL2 small,
Okay.
so do you get these kind of relations, which would simplify slightly the calculus?
If I act on a, well, so simple, so like for instance, the fundamental representation of small quantum SL2, which is the vector, the two-dimensional one, so the braining on it naturally satisfies the scale relation.
Yeah.
But as soon as you go to other more complicated, so if you do and this is kind of a generator for in some sense for the category of modules. So you could do everything using scale relations. This is everything. So I'm thinking now about the three-dimensional construction. So there is a work we did, not with Anna, but with Jun Murakami, and it's about a skein construction of semi-simple, non-semi-simple quantum invariants kind of related to this recipe in the three-dimensional case, and it's all done using just skein relations. But this is not immediately the thing you would get here, because to obtain that version of the invariant, an ingredient here is missing. And this is probably a further direction, future direction of research, to include in this construction so-called modified traces. So when you do three-dimensional topology, there is this magical algebraic structure called the modified trace that in the non-semi-simple case allows you to turn constructions which unfortunately usually boil down to previously known invariants. So if you start from non-semi-simple small quantum 2, you have a recipe for constructing an old, a recipe that dates back to the 90s to construct invariants of 3 manifolds, TQFTs and stuff like that. Well, not really TQFTs because you have an obstruction. But you have a recipe, and this uses non-semi-simple data, but the result, the output, turns out to be the same you would get from the classical semi-simple construction of Witter, Shtikin, and Turaev. So something previously known. And in order to get something different, you need to include modified traces. So the skein construction models the modified trace version of this construction. For the moment here, modified traces have not been used. It's kind of a next step.
Yeah, so there is a Kaufman-Radford invariant that is constructed from the small quantum group in a very similar way. You also put dots at the crossings, and you collect them together, and you evaluate them against the same left integral. And you get an invariant that is not equivalent to Reshetikhin's Turaev invariant.
It is up to multiplying by the order of, by the rank of the first homology.
Well, anyway, you get a different.
So it is either that multiplied by some non-zero number if you have a rational homology sphere, or it's 0.
Right. So, but so how is it related? So is this one a refinement of that one? Because what is missing in that construction, with respect to yours, it's those dots corresponding to lambda.
This is precisely the thing. So in the factorizable case, you factor through this category here, and the invariant for closed 3 manifolds there is precisely the one you're thinking about. But in the non-factorizable case, this doesn't factor through 3-dimensional. And again, like the Henning-Kaufman-Radford invariant is kind of so there were interesting constructions related to that approach, like mapping class group representations defined by Lyubashenko and Kerler. But the invariant for 3 manifolds turned out to actually be very close to with and restricting to right, just either 0 or with and restricting to right. And there is an additional ingredient to add into the recipe, which these modified traces, that produce an invariant that does not behave at all like with and restricting to right. It extends to TKFTs. These TKFTs have new properties, so kind of
Okay, more questions?
Sorry, I'm a little lost. Whether these are all oriented or unoriented?
oriented. This is nothing is oriented here.
All the things are non-oriented.
There is an easier algorithm I could have told you about if I oriented things. But yes, if you orient things, you're allowed to consider orientations. If you wanted to consider orientations, then you would need to prove that for closed component, it doesn't matter how you choose the orientation. And open components should always be oriented like this. And then you don't need to bother about this kind of, you don't need to bother about this kind of thing. And you also don't need to bother about this kind of thing. You just need to encode differently cups going to the left and to the right. You distinguish the right going ones with a pivotal element. But anyway, so this is not oriented for what I told. You can orient if you want.
All right, more questions? Maybe somewhat provocative question. You showed us some sample calculations. So how far is it from calculating your candidates for counter examples, or what's, is it just too many crossings, or what?
For the moment, it's too many crossings. So if you have computational power to do the computation, you have all the ingredients. You have presentation. The problem is, so it happens often that like, as soon as you start doing more complicated computations in quantum topology, since things are exponentially growing in the number of crossings, so the cost of computing things, it rapidly becomes.
So even for some smallest r, which is by the way, what is the smallest r? Which is
well, okay. If you get 3, yes, so right. If you want to do 4-dimensional, it's 4.
Okay, and then so. For r equal to 4, it's impossible to do the candidates.
So I haven't tried, but it's clearly so computation I've done up to now involved and in that one, so I maybe can show you again that the. Yeah. So I'm not sure. No. So I think tackling these kinds of computation is surely the goal. So you could try to pass. So this is related probably to the question that was asked before. You can try to pass to the category of representations and kind of use fusion rules and decompose things. So this is something that is kind of in progress. We need to work on it. For the moment, is not the algorithm I've given you now, but just doing what I've told you now with this number of crossings, it's kind of very, yes, it's not doable at the moment.
But in principle, your conjecture is that, like for instance,
if these give different outputs, then you disprove the Andrews-Curtis conjecture, and you answer no to this question. Mm-hmm. So you just need to be able to plug everything I've given you into a machine that spits out the right number, and.
What's the simplest example when your invariant really distinguishes one handles from two handles? So if from one of your components, from one of the one handles, just remove the dot.
Yeah. Okay.
So what would be the symbol? Because the three manifold is the same, right? Right on this one?
Yes. So add a dot here, and last slide.
And it's zero frame, right?
Yes, zero framing on both. So with this version here, it's always 1. Without the dot, it's either 1 or -1, according to the parity of R. So choose R to be a multiple of 4, and you get -1. So this is distinguished.
You said that it's possible to go higher rank, is it?
Higher rank? Yes, sure.
So here you can take any R and you get interesting results for R divisible by 4, right? So if you go to SL3, what are the conditions for R?
There are similar conditions that we've not figured out explicitly, like in the SL2 case. Yes, so they are kind of so you need to look when the R matrix is factorizable. So you need to compute the double of the monodromy matrix, and you need to.
There is a paper of Lyubashenko from the 90s where
Yes,
this
yes.
question is resolved.
Exactly. Yes, there is. So he gives an arithmetic condition on R, which is less explicit than what I've given you, I think, and the formulas I've given you. But yes, you're right. So this paper of Lyubashenko you're thinking about contains many details.
If instead of +1 you get ±1, it's kind of, it's not very far, right? Because there's also signature or something, or maybe something else, some minimal information about the 4 manifold, which you grasp. But can you get, say, 0 somewhere, where for 3 manifold it's non-zero, or something that I will really see, kind of, to be assured that you actually see the 4 manifold and not the 3 manifold plus something very...
It's a kind of inverse problem. You're saying this invariant should be this, right? Find...
No, just to be sure that it's not going all over again, you know, for 3 manifolds plus tiny something.
Sounds like string theory, right? You're given the answer, you kind of...
So I maybe will think about your question and try to tell you an example. So you're looking for a situation in which, by removing a dot, you pass from having a non-zero scalar to having 0.
For example, yes.
Okay.
Something so that I will really see that, you know, it's different from just purely 3 manifold invariant plus tiny addition of
I think
something. No, it's probably more serious.
I need to think about this.
Okay.
Thank you for your question.
Any more questions or comments? If not, well, thank you.